Cristián Simonetti is an assistant professor at the Programa de Antropología del Instituto de Sociología de la Pontificia Universidad Católica de Chile and an honorary research fellow at the Department of Anthropology, University of Aberdeen in Scotland. His research concentrates on how scientists studying the past understand time and space, the topic of a monograph he is currently writing with Routledge titled Sentient Conceptualizations. He is currently involved in the development of collaborative inquiries across the sciences, arts, and humanities with the properties of inorganic materials such as ice and concrete. So, Cristián, adelante.
Thank you.
It's your time.
Thank you all for being here, and let me put my PowerPoint. Was that my PowerPoint? I'm a bit lost here. No one. No. Yeah, this. It's all very confusing. There we are. So, the Anthropocene has opened unprecedented dialogues between the earth sciences and the humanities, as I was telling a moment ago, that defy some basic assumptions on which Western science rests. Long and slow geological processes have started to overlap with short and faster processes that characterize human existence. However, a gap currently persists between natural scientists and scholars in the humanities as they concentrate respectively on the material aspects of environmental change and the ways humans signify them. Challenging this tendency, my aim in this presentation is to explore how environmental change has been understood in science and engineering by engaging with the properties of materials. I do so by concentrating on materials that share a capacity for solid fluidity, a paradoxical aspect common of contemporary environmental knowledge, where hard facts have progressively mingled with soft politics. Before I address this, let me briefly pay a closer look at the Anthropocene. Despite its promises, the concept of the Anthropocene has not emerged empty of criticism. Its global narrative has sparkled the attention of a number of scholars whose cautionary remarks bring awareness to how scientific discourse on climate change tend to rely on homogenizing words such as we or human, which have the power to dilute responsibility and hide the complex and multiple environmental stories that exist in this era. Perhaps humans are not all the same all the time, in that not everyone shares the same level of responsibility. From another angle, the promising reencounter of the sciences and humanities offered by the Anthropocene should not be seen as a guarantee for the enactment of new disciplinary ties, especially knowing how interdisciplinary endeavors lead only in limited occasions to novel objects and fields of inquiry. Part of the challenge lies on the need to tackle the tendency among geoscientists and scholars in the humanities to concentrate respectively on material and meaningful aspects of environmental change. From the humanities viewpoint, the current environmental crisis pushes scholars to move beyond the enchantment with the social in which the scientific study of humans was born at the turn of the last century, while attending to material dimensions traditionally studied by natural scientists. This material turn, as is often described, calls to rethink not just sociality, but basic understandings of matter across the sciences and the humanities, particularly the idea that the material world is composed by inert substances. Defying the anthropocentrism on which classical political theory is built, such intellectual endeavor holds in itself a radical ecological agenda, in that the image of a passive world waiting to be controlled by humans has facilitated earth-destroying fantasies of conquest and consumption, such as the one Andres was describing in Antarctica. Western fascination with human exceptionality has prevented us from acknowledging nature's recalcitrance and the fact of technological failure in the attempt to control nature, which from the viewpoint of science and engineering historically translates into an ethics of material where material environments are simply at the service of humanity. Human exceptionality has stopped Western science from realizing how the history of humanity mingles with the history of things, as both are mutually implicated. Yet, humans are not alone in the encounter with geological phenomena. Our kinship ties extend well into the other than human, on which human existence currently depends, questioning once again our supreme place in history. Following Ingalls' critique, we will hear later on, of the emphasis on finished artifacts in studies of material culture, often at the expense of the constant flux of energy and matter that makes them possible. A true ecology of materials requires attending not just to how human sociality mingles with material culture, but more importantly to how both link as they participate in life-giving processes. In this view, no object will stand solely on its own, but will constitute what Heidegger termed a thing, in contraposition, that is, gatherings of materials into which our lives are drawn. In what follows, I wish to concentrate on an aspect that has hugely contributed to the static understanding of matter in modern science, namely a punctuated view of change sustained on an understanding of solid and fluid states as mutually incompatible. Let me start by paying attention to an image I took from a publicity campaign of the Bank of Chile, which recently opened a branch in the Center for Innovation. As you might recall, or some of you might recall, our talks today were originally meant to occur inside that building. But due to the number of encryptions, we decided to change the event to our current location. Please allow me to transport you there, with your imagination, to the Center for Innovation at the entrance of Campus San Joaquin, this campus, known for its architectural and environmental properties designed by Alejandro Ravena, who last week was awarded the famous Pritzker Prize. Its monolithic structure, made of concrete, not only highlights traditional tropes in modern architecture, but also stands for sustainability, in that its thermal properties are meant to reduce air conditioning by 40% in the summer. The publicity displayed nationally enhances the strength of the bank by showing two concrete buildings, alongside the image of a frozen glacier solidly standing against the passage of time. The selection of images in this wisely crafted picture is certainly a powerful one, knowing how Chileans have been historically marked by both ice and concrete. Chile, one of the most seismic countries in the world, adopted reinforced concrete at the turn of the 20th century as a standard in construction. Glacial ice, on the other hand, dominates the Chilean Patagonia, where the Andean mountain range extends all the way into the sea and back out into Antarctica. The irony of these two powerful photograms, frozen in time, is that both ice and concrete no longer remain still. The case of ice is clear in that glaciers are melting at unprecedented speed. The recent instability of concrete, the second most used material in construction after water, is significantly more obscure. Practically unknown to most city dwellers, concrete is responsible for between 5 and 10% of the total of carbon emissions. This contribution, invisible compared to that of other large emitters such as the flying industry, makes concrete a familiar stranger of modern life in the Anthropocene. Although concrete's unique combination of strength and malleability was meant to provide a solid infrastructure for the quick spread of modern lifestyles, its permanence and sustainability have been questioned. Concrete has contributed to another global acceleration, namely the one that is now responsible for the melting of glaciers. Accordingly, concrete and ice are part of the still-to-be-written history of modern life in the Anthropocene. Ice, a victim of global warming, is often portrayed as an endangered species. Concrete, a recent product of modernity, is a perpetrator of this environmental crime, or one of the perpetrators, standing alongside other giants. Curiously, these two substances are often described with similar oxymoronic terms that make justice to climate recent instability. In the history of Western science, they have both been regarded as liquid rocks. This property, I believe, makes concrete and ice excellent materials to think with the governance of inorganic substances in the face of the current environmental crisis. As in the sudden melting and acceleration of our supposedly stable modern lifestyles and climate, these two substances are at times both solid and fluid, properties that science and engineering sometimes struggle to reconcile. A controversy around the movement of glaciers between James Forbes and John Tyndall illustrates the tension in the understanding of ice. Forbes, one of the first to embark on a scientific description of the movement of glaciers, suggested, following an old analogy, that glaciers behave like meandering rivers. The idea was grounded on the observation that the central part of a glacier moves, when it's turning, moves faster than the edges, while the inner parts of a curve move slower, all of which involve the deformation of ice. Explained at a molecular level, ice was seen as having a capillary structure which allowed water to infiltrate, making it plastic. This became known as the viscous theory of glacier motion, developed mainly after Forbes' studies of the movement of the mer de glace in the Alps, in conversation with other pioneer glaciologists, particularly Agassiz. The young John Tyndall, a distinguished Victorian glaciologist and renowned mountaineer, embarked on a tarnishing of Forbes' reputation, including serious accusation of plagiarism. Following a masculine tendency in glaciology to validate knowledge through heroism and physical exertion, like the one we saw in Antarctica, Tyndall made several alpine campaigns, including a journey to the mer de glace, to refute Forbes' ideas. Tyndall's main target was the viscous theory of glacier motion. He argued the theory was fundamentally counterintuitive. In Tyndall's words, and I quote, "This viscous theory is so directly opposed to our ordinary experience of the nature of ice as to leave upon the mind a lingering doubt of this truth." Applying insights from Faraday's famous experiments on ice, Tyndall argued that glacial motion did not result from a semi-fluid condition, but from a process of fracturing and rigidation. Faraday's experiments involved pressure and putting pressure on blocks on ice and how they glue again, become one solid piece. Or this famous example of the wire, which is a bad example. I can explain afterwards why. The way you put the wire with weight, and the wire will go across the ice, but the ice will stay as one whole block. According to the historian Frank Cunningham, who wrote a summary of the debate, there was no adjective available at the time to describe what Forbes had in mind. Nonetheless, following Cunningham, what Forbes did not do was to suggest, and I quote, "Ice was at times one substance and at times another," which according to Cunningham will count as unscientific thinking. For Cunningham, fluidity and solidity were ultimately incompatible. This debate reveals in practice the paradoxical character ice has acquired in science as soon as it's set in motion, a problem that currently survives in glacial dynamics in what has been described as the unresolved sliding problem. Clearly, I'm in no position to solve the mystery of glacial motion, especially knowing my limited comprehension of the physics. My humble hope is to illuminate the debate by pointing at the resemblance the debate shares with how change has been historically conceived in Western science. The oxymoronic nature of ice relates to two antagonist models of change. The first model, relating to the movements of solids, therefore changes in position, is often associated with Aristotle's discussion of xenon paradoxes in the physics. The second, related to the movement of fluids, therefore changes in composition, often refers back to Heraclitus. Unlike solids, fluids can accommodate their shape to their containing surfaces. Accordingly, while changes in position are punctuated, changes in composition are continuous. Furthermore, changes in position involve a view of space as a homogeneous medium where locations are simultaneously placed and movements are reversible. For changes in composition, space and time are inseparable in that movements occur in a world in constant formation. Although physics have moved significantly from classical dynamics, embracing irreversibility in nature, as Prigogine and Stenger suggested decades ago, the tensions between these two images of change are not part of an old and obscure debate within the fields of glacial dynamics, but seem generally to characterize contemporary environmental science. Take, for example, the crucial distinction climate scientists make between climate and weather. According to the World Meteorological Association, climate is understood as an average over 30 years of the constant variations in weather phenomena. Accordingly, while most people will have access to weather phenomena, as we experience daily changes in temperature, humidity, and precipitation, climate, including indigenous peoples, of course, indigenous communities, especially in the Arctic, climate is a byproduct of scientific measurement, therefore beyond everyday perception. Knowledge about climate requires a distributed set of instruments capable of measuring variations in temperature, humidity, and precipitation over long periods of time and across vast distances. Furthermore, signals need to be averaged and displayed in dotted graphs like those that compose the recent summary report of the Intergovernmental Panel on Climate Change. Originally invisible to the senses, climate becomes visible in a representational sense. Interestingly, this view of climate change as composed by a series of static average dots plotted on a graph coincides with an image of climate history as composed by distinct punctuated moments. One of such moments is the Holocene, the stability of which is supposedly behind the flourishing of the human species over the past 12,000 years. The nostalgia of such views survives, for example, in how scientists currently lobby to engineer the atmosphere, hoping to keep it within, and I quote, planetary boundaries they themselves have created, based on what they envision is safe for the continuity of human existence on the planet. More than the Earth's atmosphere, such understanding of climate change would resemble closely the contemporary indoor climates in which scientific ideas are currently produced. Often sealed within concrete structures, these environments are manipulated at will following the punctuated parameters of a wall thermostat. Countless examples could be added to these retrospective efforts. Painting mountains to restore glaciers or de-extinction to reinstate dead species are two more nostalgic attempts to revert us back to a static image of nature at the dawn of civilization. Furthermore, looking into contemporary discussions on the Anthropocene, it is possible to see how this punctuated understanding of history is also present, for instance, in how current debates on the origin of this new era are marked by an emphasis on fossilization. Let me explain. According to the Anthropocene Working Group, only signals that are already buried in stratigraphic sequences clearly identifiable across the globe are candidates to securely tell us when the Anthropocene started. Signals need to become fossils before society is allowed to take action, a process not just conservative but extremely retrospective in nature. In a rather literal sense, the production of solid facts has been going at a radically different pace from soft-political action. It is worth noting how this retrospective view of climate history is grounded on a traditional understanding of time in the geosciences, according to which Earth history would result from the vertical superposition of flat horizontal grounds. This view has resulted in a dissociation of time and space into vertical and horizontal dimensions. In it, horizontal movements are across homogeneous surfaces that are mapped from a synoptic bird-eye view that contemplates space as if from everywhere at once. Vertical movements, on the contrary, take place across surfaces, as if scientists could travel in pure time, in search for the regional platforms from where to narrate the histories of the Earth, life, and humanity. These particular platforms will mark disciplinary boundaries for sciences that excavate the object of study. The case of archaeology is particularly clear. A discipline well-positioned, or particularly well-positioned, we might say, to talk about the encounter of geo and human history, which in recent years has actively engaged in debates on the Anthropocene. The following figure is an example taken from Harris, an author who is recognized for having contributed to the modernization of archaeology through the establishment of stratigraphic methods. The same methods currently being proposed by a number of authors as definitive in establishing the start of the Anthropocene, including Harris himself, in a recent multi-author publication on archaeology and the Anthropocene. In the image, time is represented as a series of superimposed platforms connected with a rope. Each platform represents a period in the past, a timeless surface on which life was once lived at a particular time. Like a stage set empty of furnishing features, objects, and people, these perfectly homogeneous platforms resemble a cartographic abstraction. Ordered sequentially from bottom to top in an upward gravitational accumulation, surfaces start with what in British archaeology is known as the natural soil. Represented here as a black box at the bottom. Can you see? Hope you see. There is a black box at the bottom. Perhaps those who are in the front row can see it. But the sequence starts with this black block, the natural soil, the soil the archaeologists never excavate. Although following its context, this soil often remains untouched in excavation, as it marks the initial ground where human inhabitation started at a particular site. Anything beyond this point will fall under the jurisdiction of those in charge of studying nature, namely geologists. Moving up along the road of time, we see how the present stands solidly at the top of the sequence, an image matching modern narratives of progress, including those that granted earth sciences their status as a modern discipline, through the careful establishment of stratigraphic methods. Returning to concrete, it is worth noting how this material, the most important substance in the building of modernity, has contributed to this view of progress where modern values are meant to stand solidly above tradition. As recent ethnographic and historical research on modern uses of concrete suggests, the making of concrete structures is dominated by a tendency to craft perfectly smooth surfaces, a flattening, touching at straight angles, like those that compose the vertical sequence of platforms in Harris' image. The gestures responsible for crafting those surfaces will follow an impulse to create new baptismal grounds that coincide with modernity's claim on the present. This claim, it's worth noting, will be enhanced by concrete status as a modern material. Patented in the 19th century by Joseph Aspiding, the rediscovery of hydraulic concrete not only helped England to renew its ties with ancient Rome in Victorian times, but also provided the illusion that vast geological processes could be artificially compressed in a laboratory. Engineers had somehow managed to turn on history, mastering the secrets of deep time. Seen from the viewpoint of the vast spreading of concrete in the name of the satinization of urban environments, concrete suffocating surfaces not only creating a last sense of control over nature, but also contributed to literally distance modern from its traditional rural origins. However, concrete status as a recent product of modernity has always been unstable. Concrete's supposed aura of artificiality suffers from both its dependency on manual labor and its earthbound origin into ancient volcanic activity. Furthermore, despite its their promises of durability, concrete structures are neither impervious to decay nor impermeable, aspects the cement industry has been keen to conceal. Although historically portrayed by the industry as stone of an artificial kind, concretes are incapable of lasting as natural rocks do, which according to Prentice, in his geological account of building materials, came as a complete surprise to architects and engineers at the turn of the 20th century. Unlike them, the news became unsurprising to geologists. whose expertise lies historically on a profound awareness of the slow but constant formation processes responsible for the creation of natural stone. The later can be observed, for instance, in what is traditionally regarded as the first geological treatise in the history of science, namely Stenos Prodromus, narrating the geological history of Tuscany through the existence of marine fossils buried in land. As its subtitle suggests, Stenos' essay constituted an inquiry around solid bodies enclosed by a process of nature within a solid. If you allow me to paraphrase, fossils buried in stratified sequences. Solids within solids. While engineers might aim hard to defy the passage of time, the cracking of concrete surfaces is ultimately inevitable. Given enough time, all concrete structures return to rubble, where their current permanence depends on extended practices of care. Concrete's fluid solidity is again an aspect the modern building industry has struggled to reconcile. Yet, the promise of durability that characterized modern uses of concrete seems to have influenced also geological thinking, bearing witness once again of the fact that the material world we inhabit furnishes some of our most intimate ways of thinking. Concrete is not just by far the most significant material in the building of modern lifestyles. More radically, it is perhaps the most obvious candidate for signaling the origin of the Anthropocene, bearing in mind the requirements of the Stratigraphic Commission in London. Particularly the need to identify a single marker in stratigraphic sequences on land, the Greenland and Antarctic ice sheets, or the bottom of the sea. Think of the vast expansion of megacities such as Dubai or Los Angeles. Today we produce the equivalent of 15 times the San Cristobal, and rumors are that China alone produced more concrete between 2011 and 2013 than the US in its entire history. Imagine also we were to extend the proposed layer to all the artificial surfaces humans have created or crafted in the land or on the land outside urban areas, as they source the necessary ingredients to manufacture concrete. The colossal creation of concrete surfaces over the past century, primarily across the northern hemisphere, makes concrete not just a suitable marker, but one that holds the potential to work without erasing the historical inequalities that exist between nations in terms of environmental responsibility. Production and consumption of concrete across nations correlates almost perfectly with the World Bank developmental indicators. Yet, regardless of the decision of the Stratigraphic Commission, there should be no doubt concrete holds a unique place in the constitution of modern life in the Anthropocene. Accordingly, it is unsurprising to acknowledge how the manufacture of smooth concrete surfaces has contributed to generate the image of Earth history described here, marked by the superposition of solid blocks like those commonly found in the DIY stores. DIYs like do-yourself, Home Depot, Easy, etc. These are the same blocks that, from a more explicit architectonic angle, currently dominate the ways historical processes are understood in Western academia as we speak of the building blocks of the universe, life, and the mind. And now I move to some conclusions. Ice and concrete have unveiled the tensions between fluidity and solidity in which science and engineering have historically found themselves as they try to govern the inorganic in the face of the current environmental crisis. Although we might believe these tensions belong exclusively to science and engineering, clearly the humanities have not escaped from them. Take, for example, the temporal dichotomies that have proliferated in continental philosophy since the turn of the last century, including, for example, Bergson's succession versus duration, James and Husserl, scientific versus spacious present, or Heidegger, time and temporality. They all highlight a distance between fluid experience and solid measurement. Similar has been the fate of space, time's traditional antagonist. A recent example is in how Doreen Massey liquefies space in response to Bergson's static image of it, borrow from Kant. It is as if no one has escaped from this oxymoronic syndrome, as we might call it. Western minds seem incapable of holding the image of a fluid solid substance, changing simultaneously both in position and composition, or compass action, to use a term borrowed by Donna Haraway. As Tyndall claimed, it feels counterintuitive. But what would it be? What would it be if we start? Well, what would it be to start? With an ontology where fluidity and solidity are not mutually incompatible properties? The ways the Inuit of West Greenland engage with their cryogenic landscapes offer some clues. Unlike our nostalgic views of change grounded on a desire to recover past climates, the Inuit will orient themselves primarily towards the future, in that children are brought up from an early age or from birth to expect the unexpected. Acquiring personhood for the Inuit is to grow always prepared for variations and foreseeing the world as one of constant surprise. Accordingly, while Western science discovers change retrospectively using data that has been already gathered, aiming to subsequently make predictions, for the Inuit, climate change is not an entirely novel phenomenon. A distinction introduced by the anthropologist Mark Nuttall clarifies this contrast. According to him, and I quote, people in the smaller hunting and fishing communities all around the Greenland coastline consider the environment to be in a process of becoming rather than changing. Elaborating on this distinction, we might say that while changing science results from representing punctuated states, becoming for the Inuits results from feeling continuous disequilibriums. From the viewpoint of ice dynamics, such disequilibriums would be consistent neither with Tyndall's melting and regulation nor Forbes' pure flow. Continuous disequilibrium is much more compatible with variations in rhythm. According to Henry Lefebvre, rhythms result from the simultaneous action of both difference and repetition, a process where time and space become mutually implicated. Accordingly, in a world determined by rhythms, there will be neither solids nor fluid pure states. Alternatively, there will be no such rhythms. Interestingly, this is consistent with how indigenous communities across the circumpolar north have been reporting their experience of climate change as things coming out of sync. Sea ice and species are respectively receding and migrating earlier than usual. What the Inuit are experiencing are not punctuated contrasts, but the rhythmic fluctuations of a solid fluid world in constant becoming. Imagine for a moment what would it be to build an entire research program in science on such forward-looking image of climate history, or what might be called climate becoming as opposed to climate change, or climate continuity as opposed to climate change. To do so, we will need to start by rejecting any strict separation between experience and measurement. A reality not far from contemporary climate science, as scholars are finding it progressively harder to hold their key distinction between weather and climate. Furthermore, such account of climate history will make futile any attempt to signal humans as standing alone against nature, as it occurs with anthropocenic narratives, where causality often points from humans to the environment. Adopting Barrett's ideas on the relation between matter and meaning in physics, our point of departure will probably be an ontology of entanglements. The Inuit notion of sila beautifully captures this last point. Referring indistinguishably to both weather and climate, sila is translated as breath of life and the reason things move and change. It also means intelligence, consciousness, or the mind, and is understood to be a fundamental principle underlying the natural world. Accordingly, lack of sila will mean either people or the environment going crazy. In the words of Nuttall again, and I quote, "It is an all-pervading, life-giving force connecting a person with the rhythms of the universe, integrating the self with the natural world." The emphasis on breathing experience is particularly powerful in this context. Often I notice breathing allows us to become one with the environment. While inhaling, allows for the atmosphere to come into us. Exhaling releases part of us into the atmosphere. No other process in human equals breathing, rhythmic exchange with environment. Through breathing, we become indistinguishable from our surroundings, including all the microbial life on which human existence ultimately depends. Sila is not just here and there, in and out. It holds together the entangled web of life, including the symbiotic strands we, for instance, share with microbes, which neo-Darwinian accounts of evolution have been unwilling to acknowledge. Evolutionary biology has tended as well to compress species into average dots, following the paginator of the fossil record, with the result that evolution is somehow divorced from development. Perhaps in a world of solid fluids marked by constant rhythmic transformation, not only objects will turn into things, but no self-contained organisms clearly distinguishable from its surrounding will exist. Thank you so much.
Thank you. Thank you very much for your presentation. And we have some 10 minutes before coffee break to get some questions, comments on Cristián's presentation. So please. We have the first one.
Chris, thank you very much for your presentation. It was very thought-provoking. And it brings to mind things that we spoke about during the week. And it brings to mind a question that I know you've been asking and we've had an ongoing conversation about, which is you say that we could start from an ontology in which fluidity and solidity are not mutually exclusive. And then you talk about Barad, Karen Barad later in the paper. So Karen Barad's point, from what I understand, is that the two states exist, fluidity and solidity, at a kind of particle level, but they are nonetheless incompatible. You can't be one and the other at the same time. You can, but the same thing can be one or the other. So how are you conceptualizing exactly this? Could you talk a little more about that?
Yeah, absolutely. Well, we have been engaging in this quite intensively over the past year and a half, the following year. feels like a long discussion. The past day and a half, and well, a couple of things come to mind. How something we mentioned earlier today. How for geologists there is no solid as opposed to fluid state. They will talk about highly viscous fluid. So if we, you can all hear? So if we picture the thing as a continuous, then nothing will be at the poles, but everything will fall in between. And that makes perfect sense regarding what I introduced here. Well, Karen makes this point in a critique of representationalism in science about this famous paradox, which matches in a way some of the things I've been discussing here with regards to eyes, that electrons could behave either, depending on the experimental conditions, could behave either as particle or waves. Well, it's a long explanation to make explicit what are the experimental conditions, but my feeling, I know what's the point in Barrett's argument, which is a critique of representationalism and the idea following both physics philosophy of matter, that you cannot separate the observer from the observer. And that all makes perfect sense. But let's say we buy the critique of representationalism. What else is to say about the world? And my wonder And well, Karen Barrett was one of our invited speakers, but unfortunately she couldn't come for personal reasons. One of my wonder is it this just the artifice of how measurement is carried on in science, or whether we are talking about the properties of reality? So what it is to say that particles are either in one world, and the multiplication of universes is almost a standard now in quantum physics. How many universes are we meant to have? And then there is a paradox here, because on the one hand we have been multiplying the universes, but on the other hand, Karen Barrett suggests that quantum laws should apply to all levels. And there is this common assumption that Newtonian physics applies to our scale, well, quantum physics applies to the minuscule world of particles. But if we are going to hold that continuum, then is it not counterintuitive, or is it not against the idea that we should somehow feel, or there should be a dimension in which we should participate of these multiple universes? And it seems that when we think that there's a universe in which things are solid, and another at the same time, and perhaps at the same time in space, where there are fluids, then that becomes a problematic contradiction itself. So what if to start with, things fall always in this continuum? And even at the level of the movement we experience, there would be no such thing as changes in position. So when I move something, it's always a change in composition at the same time, knowing there is a continuous exchange of energy and matter in the friction that goes on as the object moves along a surface. So then that would be my point. But of course, again, I'm here, although I'm sounding very convincing, I know very little about particle physics. And I'm in no position to make any serious contribution, I believe, to particle physics. You have a question?
Let me ask you about this. You by the end of your presentation, you went to biology or biological evolution, and when you were talking about the punctuated change, I remember James Good theory of evolution, while the opposite, or maybe a different approach, is the Darwinian with the gradual change. But which kind of biology or biological evolution you are thinking of, and which author or work you can suggest for this new idea of change in the physical world, but also in the biological world? And I'm not going to go further on this separation. But
I've been, of course, very much influenced by Tim's work on evolution. And the conversations that happen at some point with Susanna Yama, and the emphasis or the research program on epigenesis, a whole attempt to somehow put together once again evolution and development. Because if we think of the image of a solid platform, where history is narrated as a superposition, the same has been applied in biology when we think of how Darwin thought of evolution. Actually, his diagram, the lines in his diagram, he thought of each of the lines as a layer in the fossil record, so a stratified sequence. So it seems that the tree of life is superimposed to this stratigraphic view of becoming. And in that view, we move either horizontally in space out of time, or we move vertically in time outside of space somehow. And that's very problematic, and that matches perfectly how he divorced evolution from development. So in the idea that, and that happens nowadays in mainstream neo-Darwinism, genetics in general, that we believe that organisms inherit their specifications in advance of the content of the environment. So for example, I had my I was spending time, and my poor little nephew was accused of inheriting a voracious taste for cakes from his grandfather. So he was very good at eating cakes, and someone at the table said, He really resembles his grandfather. So it is this idea that somehow we inherit specification, taste, desires, before we actually taste the actual cake. Before actually we feel what it is to have it in your mouth. And that's basically what is behind neo-Darwinism. And it justified a number of research programs. For example, in psychology, separating twins and see how the environment affects them. Bearing in mind that in this logic, they share the same genetical inheritance
background.
So, and this is something Tim has argued, that in a way we need to, when we put evolution and development back together, we need to somehow merge or blur the illusory boundary we have drawn between innate and acquired properties. But then when you think of that, when you think that evolution is necessarily a process that happens in an environment, then there are many other authors who have been thinking of this and proposing a different view of evolution, like, for example, Donna Haraway it's somehow arguing that in favor of that view, where organisms are no longer self-contained entities, but entities that leak into the environment. And also what Lynn Margulis, for example, has been arguing, that the model of evolution shouldn't be an isolated organism, but rather the symbiotic relationships we build with other organisms. So we could think of the evolution of man, women, or the human species. We can think of that evolution as something that happened along the evolution of microbes, which is an entirely sensible thing to do. And then we can no longer place humans at the top of the tree. There is this image that came out after Darwin, when people were celebrating 200 years after the birth or death of Darwin. I think the birth of Darwin. No, the death of Darwin. And there was this tree of life with Darwin at the top, looking downwards. It is this funny thing that we have drawn the tree of life from one of the branches, and there's this, this mind that managed to sort of turn around history and was able to narrate the whole thing. But the curious thing is that we place ourselves at the top, which is a problematic thing to do for explaining evolution.
Okay.
That was a long answer.
No, it's fine. For me, it was very good. Thank you. Okay.
Could I just ask a question about glass? I was wondering, because glass is a supercooled liquid, technically, because its molecular structure is all jumbled up. The glass is liquid. When glass is heated, it flows, and the molecules all get jumbled up, and then it cools very quickly. So it has no clear crystalline structure. Whereas water, if it's cooled slowly and gradual conditions, will have a very clear crystal form. And I wondered if Tyndall and Forbes were having an argument, not about glassy, but about glass, what they would say about it.
Oh, I'm not sure I can answer that question. But I think the tricky thing will be to put glass in motion, and perhaps we'll need to think of glass blowing. yeah. But can you explain again, because I got lost. What would be the difference, the precise difference between...
The difference, well, technically a supercooled liquid is solid like glass when it's cooled, but it doesn't have a regular crystalline structure. So if you looked at the molecular structure of glass, you'd find silica and oxygen and whatever else is in there, all jumbled up.
Even though it's solid?
Yeah, it's all jumbled up, but it's all very chaotic. It doesn't have... It's the same with flint and obsidian, and the thing that proves that it's like that is that when you strike it and break it, you get a bulb-like formation, like a curve. When you're knapping flint, you get these curved, it's like waves going through the material. Whereas if something has a good crystalline structure and you knap it, then it will cleave along one of the crystalline planes. So
that's very interesting.
I hadn't thought about it before, but I just realized that actually something like glass or obsidian or flint really messes up our categories of fluid and solid.
I'm not sure I can answer. I would just say a couple of things I know about ice. It's such a, as you say, it has such a regular structure once it solidifies. It's one of the only solids that expands when it acquires that state, and it's very hard to melt again. So this experiment, Faraday's experiment, is wrong because apparently heat was gathered through the wire, and that's what actually lowered the melting point. I might be wrong. From what I remember, to lower the melting point of ice, you need in 1 degree, you need like 125 atmospheres of pressure. That's like being 1,250 meters below sea level. So imagine that pressure in your ear. I presume all of you have been 10 meters below, 5 meters below sea level. Imagine you're at 1,200. It's huge, and that's due apparently to its carefully aligned structure, which makes it particularly unique. And apparently glaciers do flow in a way due to the pressure, but at the very, very bottom, depending on how big the glacier, apparently the pressure is big enough to melt it a little bit. But I guess it will be an amazing comparison, as it will be with. Am I right to think glass is close to clay in some respects?
It might be.
Yeah. But anyway, that's something to give us out.
Okay, I think we are already in coffee time. So we will be back at 4 p.m. And thank you very much to Andres and to Cristián for this beginning of the seminar. Thank you, and in a few minutes